So I believe homework 5.8
Yes.
due today. Questions on the homework? $29. What does it say?
The limit is x goes to 0 from the positive side of 1 over x minus 1 over e to the x minus 1. Minus 1.
In the denominator?
Yeah. Sorry.
Ideas?
We get into one fraction.
They get into one fraction. What would that be? So what do you get?
E to the x minus 1.
E to the x minus 1 minus x all over x e to the x minus 1. Okay, what do we have now? This gives us 0 or 0, which means we can apply L'Hopital's. So I'm going to apply L'Hopital's rule here. And the derivative of the top, e to the x minus 1, derivative of the bottom, product rule, so you have e to the x minus 1 plus x e to the x. And now what? Because what do we have here? We have 0 by 0 again. Can I simplify? Not really. So I'm going to apply L'Hopital's again, and this time I'm going to have derivative of this, e to the x, derivative of the bottom, e to the x plus e to the x plus x e to the x. Now we go to 1 on top over. Alright, so x is 0, so that's 0. And then 0 here gives me 1, so I get 2. So the answer is a half. Limit as x approaches 1 from the right.
Of x to the negative 1
X to the negative
1 minus x.
1 minus x.
Yeah.
1 minus x is in parentheses.
1 over 1.
Fraction, 1 over 1.
Yeah, 1 over 1.
Oh, 1 over 1 minus x.
Yeah.
Okay. How do we do that one? Okay. So you can ln or eln, whichever. Personal preference at this point. So this is really e to the ln x over 1 minus x. Now what?
0 over 0, so you take this.
Alright, the power approaches 0 over 0. So now I can do L'Hopital's in the power, and I would get what? Huh? 1 over x divided by it's negative 1. Now as I let x approach 1, what happens?
E to the negative 1.
Let's get e to the minus 1. Right? Questions on that? Okay. Next question. 43.
Limit of x approaching infinity. X over square root x squared plus 1.
Like that?
Yeah.
Okay. There's actually several ways to do this, but which way did you try? L'Hopital's, because it goes to infinity over infinity. Right. And so you apply L'Hopital's rule, get limit as x approaches infinity of 1 divided by, what's the derivative of this?
1 over 2.
It's just x over the radical of x squared plus 1, right? And what happens to that?
Just
reciprocal.
So just radical of x squared plus 1 all over x. Now what? Huh?
Just reciprocal.
What do you say about reciprocal?
I said if you apply the L'Hopital rule, the answer will be reciprocal of the equation.
So you can't use L'Hopital's
You
rule.
cannot use the L'Hopital.
Oh. He means to say it's the opposite of the question itself, so we're just gonna come back to square one.
Oh, really?
That's what,
You mean if you apply L'Hopital's rule again here?
Yeah.
Yeah, if you applied it
It brings
again.
you back to the first one?
Yeah, the instructions said that L'Hopital's rule wouldn't work.
so.
Oh,
you would
well,
have to use another one.
someone might have pointed that out. Okay, so let's go. So you go this, let's pretend we didn't know that, like this is on a file or something, you're like doing it, and okay, so you think L'Hopital's rule is gonna work out, and you're like, ha, I got it, because this is gonna be 1, so maybe we can get something. But then you do this again, and the denominator is gonna give you 1, but this is going to give you. So now you're like, if you keep applying L'Hopital's, you're gonna just end up in a loop. So what's the trick here?
You see that the numerator is constant. If you go back to the beginning and you like put it in infinity, so it's going to be infinity over radical infinity squared plus 1. So plus 1 doesn't really matter because it's still going to be infinity. And you have basically.
Yes, but you still have the idea of infinity over infinity. How do you know one is not bigger than the other?
So
You just
the
did it.
denominator is basically, if you just get rid of that 1 plus 1, the denominator is basically just radical x squared. So it's basically x. So you have x over x, which is just 1.
Yeah, you can essentially forget the plus 1. Why does that work though?
X squared is infinity. Is it fine?
Because you divide everything by x.
One way to see this, why that's going to work out. And I'd rather you do it this way because there are situations where that sort of analysis you did, it works here, but there are situations where that sort of analysis you did can get you in trouble. So what I would actually do here is actually factor out an x squared. What's the radical of x squared? No.
Plus minus one.
Absolute value of x. Now, what's the absolute value of x in this situation? Why is it just x? Because x is approaching infinity, x is positive. Therefore, my radical x will give me a positive x in return, a plus x. Which means now I can cancel these. So I just end up with the limit of 1 over the radical of 1 plus 1 over x squared. This guy here obviously goes to 0, and so you end up with the limit 1. So this is sort of the reason why I say it can actually get you in trouble in certain situations, because you might get a negative sign being factored in there if your x was going to a negative number. So you might want to be careful about certain things like that. Other questions?
31. Limit x approaching infinity. Parentheses x minus x. Parentheses. Yes.
That's it.
That's it. We did a problem similar to that in class. What was the trick?
Factor out x.
Just factor out an x. Now what happens?
That denominator, so over 1 over
This guy here is infinity over infinity, so you can apply L'Hopital's, and you can actually show that it goes to 0 by L'Hopital's rule. Which means that this expression here goes to 1, and so this goes to infinity times 1. So the answer is infinity.
That as x approaches 0, cotangent 2x times sine 6x.
Tangent 2x times
Cotangent 2x.
times cotangent
No,
2x.
cotangent 2x times 6x.
Cotangent 2x times
Sine 6x.
sine 6x. Okay, ideas?
Sine 6x over tangent 2x.
We can write this as sine 6x over tangent 2x. That's correct. Now,
6 cotangent.
we could do L'Hopital's short. So, the derivative of the top, 6 cosine 6x, derivative of the bottom, 2 secant squared. This goes to? Yeah. You could also use the special trig limits to solve that. So this is something you could have done back in Calc 1 even. Any more questions?
19.
19.
Limit of x equals 1. X to the a minus 8x plus a minus 1
Plus a minus 1.
over x minus 1 squared.
X minus 1 all squared.
Yeah.
Okay. Right, so if I let x go to 1, 1 to the a is just 1, minus 1 gives me 0, this would be minus a plus a, so the top would go to 0, and this would also go to 0. So I can apply L'Hopital's rule. What's the derivative of the top?
ax to the a minus 1.
Ax to the a minus 1, there's a constant, so you just apply the power rule, derivative of this, minus a, derivative of this, 0. And that is 0. So you just have that on the bottom, derivative, 2 times x minus 1. Now what? I got a 0 over 0 again if I plug in x equals 1. So I'm going to apply L'Hopital's again. Derivative here,
a squared minus a
a times a minus 1, x to the a minus 2. This
over 2.
is 0 divided by 2. So now I can plug in x equals 1, right? So then this just gives me a times a minus 1 over 2. Questions? Other questions? Yes?
27. The limit is x approaches positive 1.
X approaches
Positive 1.
1 from the right.
On the right.
1 from the right.
1 from
Okay.
right. ln x and pi x over 2.
Tangent of pi x over 2.
Yeah.
That's what, like that? Okay. What happens here?
Bring the tangent to the denominator.
Hmm?
You could bring the tangent to the denominator, so ln x over cotangent pi.
Why would you want to bring the tangent to the denominator? What form is this?
0 times 0.
Right, this gives you a 0 times infinity. Right, so we have to change it to a form that's useful. And as he suggested, you can bring the tangent underneath, write it as a cotangent. And this goes to what? 0 over 0. So apply L'Hopital's, because this goes to 0 over 0. So the top is 1 over x, the bottom, derivative of cotangent.
Again, cosecant.
It's minus cosecant squared of pi x over 2 times pi over 2. Now what?
So then you get negative 2 over 5.
What's cosecant of, if I plug in x equals 1, I get cosecant of pi over 2. Cosecant of pi over 2 is what? It's 1, because cosecant is 1 over sine. Sine of pi over 2 is 1. So cosecant squared is 1. So that's just 1 times minus pi over 2, and 1 over that. So I get 1 over minus pi over 2, which is minus 2 over pi. Any questions from the review problems? The review problems for the test on Tuesday, did anyone try them yet? No? Or you just understand them all? Okay, that's awesome too, I guess. Okay, pass over your homework 5.8, and we shall move on. Yes?
I mean for the review.
From the review, okay.
Limit of x approaches negative infinity.
That's another limit question. Can't get enough. Limit as x approaches negative infinity,
And that's e to x
e to the x
times the third root of x.
times the
Third root of x.
cube root of x. Is that the,
Yes.
that's, where is this from?
Fall 2013.
So this is fall 2013 problem
3b.
3b. Okay. Ideas? As x goes to minus infinity, what happens here? ETX goes to 0. What happens here? You get negative infinity. So this is a 0 times infinity, which is useless. How do we get something useful? So we're going to put 1 in the bottom, I guess. So which one would you put in the bottom? Probably the x, the one that's easier to differentiate. All right, so I'd probably go here first. And now what do we have? This would be negative infinity divided by infinity. So it's an infinity over infinity, right? So minus infinity over infinity. And so I can apply L'Hopital's rule. Derivative of this?
1/3 x to the negative 2/3.
1/3 x to the minus 2/3. Derivative of this?
Negative e to the x.
Negative e to the negative x, which gives us
Zero to 0.
if this goes to negative infinity, what does that give us? Right, the top will give you 0. What would the bottom be? 0. What do we do now? You want to try it again? Because this wasn't 0. It's negative infinity. So this is 0 over infinity.
No, positive.
Right? So what does that mean?
L'Hopital again.
We can't do
The top goes to 0, right? Because to the minus part, this means 1 over x to the block, and the denominator is going to infinity, so this is going to 0. Here, plug in negative infinity here. This turns into a positive infinity, so it's e to the positive infinity, so this is 0 over infinity. So what's that? That's actually just 0. Right? A constant over infinity is 0. Didn't need L'Hopital's again. Actually, we couldn't apply L'Hopital's again. It's not the right form. That's it. The questions from the review? Okay, let's continue. 6.1 continued. We were talking about integration by parts, which is the reverse of the product rule, and we can now integrate stuff that we couldn't integrate before. Like x e to the x. Was that the example I did? I think that was what I did last time. Okay, so first let's recall the by parts formula. You can tell me without looking in their book.
Minus the integral of UD.
Integral of UdV equals
UV minus the integral of BD.
VDU. Right, so remember that's just something we know now. I don't know how you want to memorize it, but whatever you have to do, memorize. I used to have a way to memorize it back when I was learning this, but then a friend of mine told me the way he memorizes it, and now that's stuck in my head. Because he's like, oh, it's u times v minus the integral of VDU. Right, like he says the word video, and just sort of like, oh, that sort of sounds like VDU. So every time in my head when I write this down, I think video. So that's actually the formula. So, okay, so the idea is we need to choose a u and a dv to plug into the formula. Given the integral of a product. And we actually did this once with x e to the x. So we tried to integrate x e to the x, and we're like, oh, u equals x, dv equals e to the x, and it actually worked out pretty nicely. I also mentioned that if we had done the opposite, if I had let u equals the e to the x and my dv be the x, I'd actually end up in a worse situation, right? Because I'll actually bump up the power of the x, and that would cause trouble. So now the issue is, if faced with a random integral where it's not so obvious, how do you know who to choose to be what, right? So I will now tell you how we actually choose who gets to be you, right? Let's start. Okay. Who gets to be you? Brad Pitt. You just say, who would play me in the movie? No, that's not. How do you choose which function gets to be the u? Obviously, the other guy is going to get to be the dv. There's a mnemonic. It's called LIATE. LIATE. Like a latte, only fancier. Right? So it's called LIATE, and here's what it means. It's sort of like SOHCAHTOA, it's just an acronym for something. So here's what LIATE means. The L stands for logs. So if a function is a logarithm, the I stands for inverses, i.e. inverse trig functions, or like inverse hyperbolics, things like that. The A stands for algebraic, but basically what that means is like a polynomial. Right? They just, you couldn't have LIATE, so they just they wrote A and said, oh, it looks like an algebra, right? Yeah, so it stands for polynomial. T stands for regular trig functions. E stands for exponential functions. So that's LIATE. And basically there's a hierarchy. The guys on top gets to be U first. These guys get to be U last. So if you're looking at integrating something and you want to use integration by parts, and let's say you have an inverse trig function times an exponential, who gets to be your U? The inverse trig function, right? If you have a log times a polynomial, who gets to be the U? The log function, right? Once you're higher in this list, you get to be the U, the other guy will be the dB, right? So this is how you can choose. So LIATE, that's the mnemonic to remember. So you have to remember the formula, you have to remember LIATE, because that's going to tell you how to choose. That being said, let's do a couple more, well, more than a couple, a few more examples. Don't want to do that. Let's look at something like x times sine x. Again, going simple. X is your U, because this is a product of functions. This guy is an algebraic. This guy is a trig function. So I have an A and a T, and I think LIATE, A comes before the T, therefore my A is the U. And so here I would say U is equal to x, dV would obviously be sine x dx, du would be 1 dx, v would be the integral of sine, which is minus cosine x. And then the integral of x sine x is u times v minus the integral of v du. It becomes a plus cosine x dx. So this becomes minus x cosine x plus integral of cosine, positive sine x. So that would be your answer. Let's look at some repeated integration by parts. We're going to do a couple examples just so you see what this means, and I'll actually tell you another shortcut to deal with guys like these. Well, some of the people like these are a lot quicker. So let's say, for example, I don't want to integrate x e to the x. I want to do something like x squared e to the x. Who's my u? X squared, because I have an algebraic and I have an exponential. According to LIATE, algebraic comes before exponential. I'm going to choose this to be the u. The dv would be the e to the x dx. This means my du is 2x dx. My v is e to the x. This means that the integral of x squared e to the x dx is equal to u times v minus the integral of v du. And I have that expression. Now what? Now I'm going to have to integrate this guy. How do I integrate that guy? You're going to have to use integration by parts again, right? So now you're going to do u equals x, dv equals e to the x dx. This means my du is just 1 dx. My v is e to the x. And I'm going to do integration by parts again. I won't have space there. Let's do it over here. So here I have x squared e to the x dx is equal to x squared e to the x minus 2 times. So now it's minus 2 was in front of our integral times. I'm going to open a bracket and write what this integral is. U times v, x e to the x minus the integral of the du. So it's e to the x. So this is x squared e to the x minus 2 times x e to the x minus the integral of e to the x. Now that one I can do. So it's just e to the x plus c. In other words, this is x squared e to the x minus 2x e to the x plus 2 e to the x plus c. Or if you prefer, which I wouldn't particularly care, you can factor out the common e to the x. So either of those. So one thing you should notice is that sometimes you might have to do a repeated integration by parts. Sometimes also you might have to combine integration by parts with another kind of function. But let's first, with another kind of integral technique, which I'll show you that a little later. So sometimes you have to do an integration by parts inside an integration by parts. I call it repeated integration by parts, and I'm going to show you a shortcut that can work on some integrals like that, including this one. Let's do a weird one. So we know what the integral of 1 over x is, right? That gives you ln x, right? Absolute value x. What's the integral of ln x, though? So this is one of the ones where you're like, so I don't really know how to integrate that, and it's not really a product. Well, not that you can see. So this one, it's what you do integration by parts with, except you do this little ingenious move of considering the other function being 1. Right? You can actually do that sometimes, and I'm going to show you another example where you can do that. So if you're faced with something like the integral of ln x, like, substitution can't help me and I don't have a rule for it, and you think integration by parts, okay, what are my two functions though? Turns out, think of the other guy as being 1. So what I can do here, so if the other function is a 1, what kind of function is 1? It's algebraic, right? Constants are polynomials. And this guy is an L. So I have an A and an L, who gets to be the U? The L. So U equals ln x. Right? Which I happen to know how to differentiate that, which is 1 over x dx. My dv gets to be 1 dx, which means my v is just equal to x. Which means that the integral of ln x dx is u times v minus the integral of v du. So you take x times 1 over x dx. The x's will cancel. So you're pretty much integrating 1. Integral of 1 is x plus c. This means the integral of ln x dx is equal to x ln x minus x plus c. And that is something we know now. If you have to do with integral of ln x, I do not expect you to go through by parts. Know this. Integral of ln x shows up all the time. It's worth just knowing it. So know this. It's just another thing we know now. It's just how it goes. And in general, anytime integrals show up very often, I will tell you that it's better that you just know them. Okay. So let's do another. I'm doing examples off the top of my head right here. Because I didn't think of these. Let's say I had to do sine inverse of x. You know what the integral of sine inverse is? No, the derivative of sine inverse is 1 over the radical, 1 minus x squared. What's its integral? Again, you think integration by parts where the other function is a 1. So in this case, my u is going to be what? So 1 is an algebraic. This is inverse trig, right? LIATE. So who comes first? Sine inverse of x must be the u, which means my dv must be dx. Luckily, this is, right? This is one of the ones where you almost don't have to think about it, because you really, if your sine inverse was the dv, you're like, I'd have to integrate that, but that was the problem in the first place, right? So I actually don't know how to integrate that, so that has to be the guy I'm differentiating, right? So the derivative of that, we know, what's that? 1 over the radical of 1 minus x squared. My v would be x. So this would mean the antiderivative of sine inverse of x dx is equal to u times v minus the integral of v du. So I have x sine inverse of x minus, how do I integrate that? It's a substitution, right? I would do u equals 1 minus x squared. My du would be minus 2x dx. So this is minus 1/2 du. Gives me x dx. So this becomes plus 1/2 times the integral of 1 over radical u. How do I integrate 1 over radical u? Power rule. How do you do that? So it's just u to the minus 1/2. I thought I heard someone mumble ln of something. That's a blasphemy. Remember, 1 over doesn't automatically mean ln. It's only ln if what's in the denominator is a linear function. Okay, so let's pick this up. So now we have x sine inverse of x plus, add 1 to the power, divide by the new power, divide by the new power makes it 2, so that kills the half, and I just get
2u half.
Radical u. And my u was 1 minus x squared. So this is the antiderivative of sine inverse x. Questions? So again, as you're going to learn, when we're piling on integration techniques, you're going to realize a lot of times you're going to have to use one or several of them on a single problem, right? This is why you need to be quick. You need to recognize which technique you're going to use. We're going to pile on a lot of them. So I'm going to sort of tell you some tricks on how to organize it all and sort of how to think about it. But just get into the motions. Not all the time is this integral that you obtain is going to be easy. Sometimes you're going to have to do integration by parts again. Sometimes you might have to do something else, like a substitution, right? But we'll get to that. What about something like x squared ln x? U equals ln x, dv equals, so du equals v equals no, the powers increase. What do we do? Right? We follow the method. Right, so it's u times v, x cubed over 3 ln x minus the integral of v du. But now you're multiplying two things that are powers of x. X just cancels one of these guys, you get x squared over 3. So this would be x cubed over 3 ln x minus integral of this.
1/3 equal that, and then x cubed over 3 again.
So ultimately it's x cubed over 9. Okay, let's do examples, more. Okay, here's another fun one. E to the x times cosine x. You're gonna love this one. All right, so this is an exponential. That's a trig function. So trig comes first. You can say u equals cosine. dv equals e to the x dx. du equals minus sine x dx. v equals e to the x. So we're going to like the integral of e to the x cosine x dx is equal to u times v minus the integral of du. Minus, cancel this minus, becomes plus, and get e to the x sine x dx. How do I integrate that? Integration by parts again, right? I'm going to let u equals the sine, du equals cosine x dx. Here my dv equals e to the x dx. My v equals e to the x. And so this is going to be e to the x cosine x plus u times v minus the integral of du. So how do we integrate that guy?
Hard.
Should we notice something strange here?
No. Look at the little thing, yeah.
L'Hopital's rule is only for it.
No, the infinite loop
We're
thing.
gonna have to like add a new blasphemy to it. Trying to use L'Hopital's rule on something that's not a limit.
No, the infinite rule, the infinite loop thing.
Let's just do it all again, right? That obviously seemed to work.
Yeah.
We got the same thing again, right? It turns out that these functions here, they sort of revolve on themselves. E to the x, whether you're taking integrals or derivatives, it's going to keep giving you e to the x. Cosines are going to keep switching between sine and cosine. You're always going to revolve and get the same thing again. How do we get around it? How do we break the loop? Huh? Rewrite it how? Come again?
So there are a lot of ex cosine x plus ex sine x.
Mm-hmm.
So it will be n ex cosine x plus n.
What?
You add that integral to those.
Yeah, algebra. Right? It's sort of like you have like x equals 2 minus x. How do you find x? Just add it to the other side. Right? This guy and that guy are the same. I want to solve for this. Move it to the other side. Right? So I can literally just move this guy over. This is going to give me 2 times the integral of cosine x dx equals e to the x cosine x plus e to the x sine x. Of course there's a plus c in there somewhere. And now I just divide by the 2. So e to the x cosine x dx is equal to 1/2 of this guy. And that's how we do it. Right? So I'm just going to rewrite something so you sort of see how. Because this can happen when the function is really ugly and you might not want to write it all the time. So sometimes you look at a problem, right? And substitution obviously won't work here, and we're like, okay, we're going to use integration by parts, but you notice that the functions are just going to revolve on themselves. So you know you're going to end up in a situation like this. It's customary to just give the integral a name and just move it around like a variable. So you might just say something like, let I equals the integral of e to the x cosine x dx. Right? And so then you'd have I is equal to e to the x cosine x. This would be you just repeat that. So this would be e to the x sine x dx. And then you keep doing integration by parts repeatedly. And here you get e to the x sine x minus integral of e to the x cosine x dx. And then what you do is you just say, oh, that's what we started with. That's I. And so you'd have e to the x cosine x plus e to the x sine x minus I. Right? So usually they just write I instead of that integral because they don't want to rewrite it all the time. Then you move it over, so you get 2I is equal to blah. And so I is equal to a half of blah plus C. Right? So sometimes you can see this coming and you just know to write I so you don't have to rewrite everything again. Sometimes it might be annoying. So I just want you guys to see that. So that's another situation that can show up. Sometimes you're doing integration by parts and you actually get the original integral back. Right? But don't panic. Just move it to the other side, solve for it like you would in an algebra problem. Okay, what other situations? Okay, now let me introduce you to something called the tabular method. Something that's super useful, but when I was taking Calc 2, no one told me about that. I found this out like way after that. Why did no one tell me about this? I'm not sure if your textbook does it. I don't think it does. It's a method to integrate. By the way, things like these, I don't know if these are the official names, but I'd call this a revolving integration by parts because it revolves on itself. So there's a repeated integration by parts and there's a revolving integration by parts. And these names are just for me talking in class, so when I say it, you know what I'm talking about. I don't think those are the official names for them. So this is a method to integrate repeating integration by parts. But there's one caveat. When u goes to 0 upon repeated differentiation. Okay. So if you use something like a polynomial, right? So let me do the example we did before. Let me illustrate it with the example. And then I'll show you another one. Illustration. So integral x squared e to the x. Remember here we have to do integration by parts twice. It was a revolving, but we have to get it done twice to work. But here you'll notice that your u would have been x squared, right? Now what happens if you keep on differentiating x squared? X squared becomes 2x, which becomes 2. Which becomes 0. Eventually your u will die if you keep differentiating it, right? Whenever that's the case, you can use the tabular method of integration by parts. So you don't have to be repeating the integral by integration by parts. So here's how it works. You basically set up a table. So what's happened is you choose, you know who's going to be your u. What you keep doing is you keep differentiating that until you hit 0, right? So x squared derivative is 2x, derivative of that is 2, derivative of that is 0, right? So keep differentiating until you hit 0 in this column. Keep differentiating till you hit 0. Okay, so that's what happens in this column. This column, you just keep integrating, right? So in this case, the integral of e to the x is e to the x. Integral of e to the x is e to the x. This one's hard work. Integral of e to the x is e to the x, right? So you keep integrating until you get to the 0 level, right? Keep integrating until you get to the 0 level. One other thing you need to fix, there's an alternating sign thing because the integration by parts formula has a minus sign built into it. So eventually you're going to have a minus times a minus if you keep doing this. So the signs alternate, and you start by putting a plus on this level, right? You always have a plus here. Always plus here. And you alternate. So this is minus, that's a plus. Okay. Now, multiply across the diagonals. Right? So you start from here, multiply here. So you do this, you get x squared e to the x. Right? You apply the sign after you do the multiplication. So this is a plus x squared e to the x. And you continue in that pattern. 2x, here you get 2x e to the x. Apply a negative sign to that. So that's a minus 2x e to the x. Here you get 2 e to the x. That level has a plus sign. You get a plus. What do you get when you add these all together? You get x squared e to the x minus 2x e to the x plus 2 e to the x. And that was the answer we had before. So, in an exam, I'm going to test who was paying attention. I'm going to be like, x to the 5th e to the x. Put that in like problem 1, part A. And watch all the people die from the algebra of expanding the brackets and doing integration by parts. Yeah, you know, you have to, the things I live for, you have to make it fun. Right? You'd have to do integration by parts 5 times here. Do an integration by parts within integration by parts within integration by parts, multiplying out brackets, signs are all over the place. Or tabular method. This is 5x to the 4th, right? Then 20x cubed, then 60x squared, then 120x, then 120, then 0. And we stop because we're at 0. This happens to be easy, just the same guy all the time. Plus sign here, minus sign here, plus sign here, minus sign here, plus sign here, minus sign here. And now you multiply across the diagonals. So x to the 5th, e to the x. Five x to the 4th, e to the x. This gets a minus sign though, so this is x to the 5th, e to the x, minus 5x to the 4th, e to the x. That's a minus. Here, I get a 20x cubed, e to the x. That's a plus. Here, I get a minus 60x squared, e to the x. Here, I get a plus 120x e to the x. Multiply here, I get a minus 120 e to the x. Plus c. Now look at how long that answer is and try to appreciate how long that integration by parts would have taken us. Like a whole 5 pages just doing this one thing. You guys can try it the long way if you prefer. I won't.
Okay.
You can just try it to see how long it would take you and if you actually get to that answer. But yeah, so if you have an integration by parts where the u eventually hits 0, you can do this method.
Why does it work?
Well, by writing out the method, you'll see it. It's just a matter of expanding brackets, and when you're multiplying, so it's like you have that u times v minus the integral of v du, and then this sort of breaks out into a u2 times v2 minus the integral of v2 du2, and then this minus gets that minus to be a plus. So by the time you hit the second level, you're a plus sign and things like that, and you multiply out, and yeah. The proof is, yeah, it's sort of algebraically intensive. You don't need to know it.
Yeah, quick question. You know how you put positive on this? Why is it negative?
Negative where?
How 5x
Positive.
plus you're dropping into it, and then you put x to the 5 into x minus 5. Would that be positive or?
No, this is right. So at first you ignore the signs until after you do the multiplication, right? So it's just x to the 5th times this gives me that, and then I apply the sign. Then I do 5x to the 4th times this gives me that, then I apply the minus sign. Right? The minus sign applies across to your result. So don't think you take a minus 20x and multiply. That's not how you want to think about it. Right? The signs hit their level. Yeah, so that's some nice. So this we're sort of going to be coming back to and building up all the time. So this is sort of a strategy you should have in your head. Strategy. Yeah, I'm slow today. So funny, I'm so tired. Like today, like every time I was like walking into the NAC or something, every time I like approach any door, I like start taking off my house keys. I have to be like, you're not home, idiot. I just want to just go home and drop him like that. Oh man, luckily I can do calculus in my sleep or we'd be in trouble. Okay, so there's a strategy for integrals, which we're going to keep building up as soon as we add more techniques. The idea is basically, try to take the easy way out.
Okay.
That's basically how you want to think about it. In general, we're going to be learning techniques in the order of difficulty, right? So pretty much substitution is the easiest one you're going to get. Integration by parts is the next easiest, you know, and it's going to build. Next time we're going to learn trig sub soon. It's going to be annoying. Then you're going to learn integration by partial fractions and all sorts of things. So idea is try to take the easy way out, which means when faced with a random integral, right, which on the final you will be, they're going to give you a list of integrals and say integrate all of these, right? When faced with a random integral, right? How do you know what you're going to do, right? Because so far we have like 3 major techniques. How do you know which one to choose? And we're going to get more along the way. One, try to simplify and apply a basic rule. By basic rule, I mean things like the power rule, etc. Right? You always try to get the easiest one out of the way. The basic rules are like the integral of x to the n is x to the n plus 1 over n plus 1, or the integral of sine is minus cosine, and things like that, right? Those basic rules where there's nothing to simplify, nothing to really do. It's just something you just know as a rule. That's what I call basic rules, right? So you face with a random integral, the first thing you gotta do, can I simplify and get away with the basic rule, right? That's the first thing you want to think about, right? 2, if you can't, think substitution. Right? If a basic rule doesn't work, substitution should automatically be the next thing you think of. Don't skip and start thinking integration by parts or something else other fancy. A lot of times substitution works in many situations here. And it's one of the easiest techniques to apply, right? And it's one that you can look at it and you can tell if you make this, the derivative is somewhere else. It's also easy to spot if you know to look for it, right? So try to apply a basic rule. If that doesn't work, try substitution next. If that doesn't work, then you move on to more exotic things. So the third would be if it's a product try think by parts. Or I don't just want to say try, I want to say think. So far that's all we have, right? We will be adding to this list soon. But this is the order in which I want you to think. Can I apply a basic rule? No. Can I do substitution? No. Integration by parts, right? That's the order in which you think, right? So when you face with an integral, just, oh, I don't know what to do. Start here. Is there a way to simplify and get a basic rule, right? So I give you something like, oh, you know, x to the 7 plus x to the pi minus e to the x over, well, e to the x would work out nice, like ln of 5 over the cube root of x, right? So it can look scary, but that's a basic rule, right? Divide into each, you subtract the powers, that's a power rule problem, right? It looks scary, but the first thing you're going to look, can I apply a basic rule? It means, can I simplify? If we have this, it's not a basic rule anymore, because I can't simplify that, right? So then I start thinking something else. So it doesn't matter if it can look scary, but sometimes the easy ones can actually get you out of the woods here, right? So that's where you want to start. The first thing, can I apply a basic rule? Can I simplify, right? Here I just have a single x raised to a power. It's easy to simplify this, right? That's the first thing I'm going to look for. And it's when that doesn't work, then I think, can I substitute, right? There's something well, 3 was if you guys had done the review, you would have realized there are some integrals that we can do now that you can use substitution on that you might not realize you can use substitution. For example, let's say I have x cubed over the radical of 1 plus x squared. Now, when I was learning Calc 2, we waited until we hit trig substitution to do something like that, and it's horrible. Substitution can work, right? So I see something like that, I'm going to think, can I use a basic rule? No, that guy doesn't allow me to simplify. I can't divide that into this, I don't know what that is, right? So now I'm going to think, can I do substitution, right? And then I think, well, if I'm going to do a substitution, what would the u be? I'd like it to be the complicated guy, right? So then I'm like, okay, u equals 1 plus x squared. And then you're like, okay, du is equal to 2x dx, right? And you're like, so I need to have an x dx somewhere in my function.
Yeah, split the x dx.
Right, it might not be obvious, but you do have the x dx, right? Because x cubed you can think of as x squared times x, right? So then you're like, okay, yeah, I can get that. This guy I just think of as x squared times x dx, right? And so now try to start swapping things out. So this my half du would be that x dx, right? So this guy here is going to be my 1/2 du. Right? This guy here, I know is my u. And then you're like, this guy here is just hanging out. What do we do with him?
U minus 1.
U minus 1. Any guy that's left over, you go back to your original substitution, right? Since u is equal to 1 plus x squared, I can literally just solve for the x squared. This means u minus 1 equals x squared. So I can just take this guy and replace with u minus 1. And so now my integral becomes u minus 1 times, this guy becomes 1/2 du divided by, this guy is just radical u. And now you're like, how do I integrate that? Still start at the beginning, Can a basic rule work? Yes, it can now. It's just powers of u. I can just divide into these guys. So this is 1/2 times u to the 1/2 minus u to the minus 1/2 du, right? Okay, so then we now just do the power rule. So this is just 1/2 times integral of u to the half. U to the 3/2 times 2/3 minus u to the minus 1/2. 2u to the 1/2 plus c. And now my u is 1 plus x squared. So 3/2 minus 2 times 1 plus x squared to the 1/2. So again, faced with something like this, the first thing I'm going to think, can I use a basic rule? Nah, can't simplify that. Can I do substitution? Well, let's try, right? It might not be obvious at first, but really think about it, right? It'll save you a lot of time, trust me. When I teach you trig substitution, and we're going to do this with trig substitution, you're going to see it'll take a heck of a lot longer than that, right? So it'll save you time. It's worth the effort of going through and thinking, can I do a substitution? If I'm going to substitute, what would I substitute? The denominator. Okay, I only get an x. I have 3 of them. Doesn't matter. Split it up, right? Then, whenever the guy's left over, you just use your original equation to solve for it, right? You get something else. It's another integral. How do I do that? Can I use a basic rule? Sure, I can simplify that. Do it. Oh, power rule. Done. Right? Another more exotic substitutions. As you're going to learn with integration by like trig sub and things like that, substitution doesn't always have to look how you think it has to look like. You just let a single variable be something else. Or you can do something like u square substitution, right? So you can let u square be something instead of just u be something, right? And it can actually save you some algebra, especially, you know, algebra is your weak point. So something like this, for example, so we went through a thing. Can I do a basic rule? No. I want to do substitution. Okay, what would I make substitution with? 1 minus x squared. Now I can see that, oh, if I make that u, I'm going to have u to the half, and I don't really like working with half powers, right? So how do I get around that? Let under here be a square to kill the radical. I could have instead said u squared equals 1 plus x squared, right? I don't just always u equals this, right? You can be a little more exotic. If this was a cube root, I can say u cubed equals 1 plus x squared, right? Right? I can sort of make things easier on myself if I don't want to deal with radical powers. So if this was like, you know, 7 and that was a 15, you're gonna have to deal with a 7/15. No, you can alter your u to kill the thing you don't like, right? So notice that it's not just u substitution. It's substitution, right? Which I spelled that wrong. This ain't English class, I'm sleepy. Okay. I said I can do calculus in my sleep, not spell. Okay? So we can do that, right? And you can sort of think of it as saying u is the radical of 1 plus x squared and then squaring both sides. You can also think of it like that. But you can just think, I don't like that radical. Let u squared be that, right? How do you think I would proceed now? After you do your substitution, what is the next step? You differentiate. How do you differentiate u squared? 2u du. This gives you 2x dx. In other words, u du will be x dx. Right? So now, I look at this guy, he's x squared times x dx over this guy, 1 plus x squared, right? So I realized, okay, I got rid of this guy. That's my x dx, right? I got rid of this guy. That's actually just u. I'm left over with the x squared, but that just means I can solve for it here. X squared would be u squared minus 1. Now let's look at the results of this fancy substitution. Now what's going to happen? The x squared is u squared minus 1. Right? X dx becomes what? U du. The radical on the bottom becomes u. Cancel the u. I don't even have a fraction anymore, much less a fractional power, right? So just by tweaking my substitution a little bit, it can pay off greatly. You understand what I'm saying? Okay, so now you're gonna, well, that's super easy. Now that's just u cubed over 3. You hardly have to think about it. Obviously that's a basic rule. Plus u plus c. And now you just replace it with your u. Now your u was actually what? It's the radical, right? In other words, u is 1 plus x squared to the half power. And then you cube that. So this is just 1/3 1 plus x squared to the 3 over 2 power. This is minus 1 plus x squared to the half power. And that's what we had before. Right? A lot easier, right? We thought it was easy before, now it's super easy, right? So things like that you should be aware of. Typically I don't see things like that in a typical calculus course, but over the years, like way after I did Calc 2, I started finding out all this. I was like, why didn't they tell me about it? Maybe they're more liberal these days and they'll tell you about it, but when I was learning, they didn't. So yeah, you can make things a lot easier on yourself. But again, it's good to have like this process of thinking. You think, can I do a basic rule? No. Can I do substitution? No. Then you think of other things, right? And there are certain things you would look for. Like if you think of things as products, you can think, oh, product rule. There are other things you'll look for. If you see rational functions, you'd probably think partial fractions first, which is a couple sections away. We'll do that. And as well as you might do something with trig substitution. So for example, let me get rid of over here. What we just did would not work for something like, so we just did what? X cubed over the radical of 1 plus x squared, right? Seems harmless enough. We're screwed. If that's a 4, this won't work out anymore. So I'd be like, can I do a basic rule? Nope. Can I do substitution? Damn it. Now we'd have to try something more exotic, which is what's in the next section. A trig substitution is what you'd have to do here. It's not that difficult to know when this will happen, which I will talk about again later. When the outside is an even power, it messes things up, basically, right? If this is a 5, we're in business again. 6, damn it. 7, yeah. 8, shucks, right? So there'll be little things like that that you'll learn what to look for when you practice enough. But you always sort of think, right? Don't just be like, oh no, it's like this is the 29th. You're like, oh my God, what do I do? Substitution, right? When you think about it, because what's going to happen is you can think of this as 28 times that x. And that x dx is always going to be there for you. And then, because it's an even power, it's easy to write it in terms of x squared, right? But if it was like already a 28, and then you put the x over here, now you have 27. Write that as a squared, you get a half thing, you get a radical in the numerator, you end up in a worse situation, right? So things like that, look out for. I'll talk about that again when we go to trig substitution. So something like that, you would use trig substitution, which personally I hate trig substitution, so it's like something I try to avoid, if at all possible. But I feel like a problem like that, most people would have a knee-jerk reaction to use trig substitution, but it's serious overkill. Serious overkill. Let's talk about, that's 6.1. Let's talk about some stuff from 6.2. Go back to trig, everyone's favorite subject, trig integrals. Let's just do some basic ones that you should know right off the bat. Integral of cosine squared and integral of sine squared. So let's look at those. Now in my day, I've seen some crazy things. I've seen people do cosine cubed over 3. Like, it's a cosine, the power rule doesn't work, right? Which again, I want to state that it's not just a random thing that I often ask you guys to actually write down rules on the quizzes. I want you to know a rule, right? It's not just me to, oh, I don't know what to ask them, let me just ask them a rule. No, I deliberately ask you the rule. It's very important that you know when rules apply, right? Power rule only applies to things like this. If your x is a trig function, all bets are off, okay? So if I see you see something like this and you go like, add 1 to the power, divide by the new power, I give you a 0 for that problem and I move on. I'm not gonna look at anything else. Power rule does not apply here, okay? So that's what doesn't work. What does work? Substitution, okay? We're thinking along the right line, so we think, do we know a basic formula for this? No. Can substitution work? How? What would you substitute? Okay, so if u equals cosine, what would happen? D would be a minus sign. Do I have a minus sign? Shucks. Substitution doesn't work. Any other ideas?
Identity.
Identity. I told you what these guys were in terms of an identity, which I think I also asked you on the last quiz. How can we rewrite cosine squared? No. 1 plus cosine 2x all over 2. Right? Or you can write this as, you can factor out the half to make it a little bit easier on your conscience. Right? Can I integrate 1? Yeah. Sure. Can I integrate cosine 2x? Right. Huh? Right. It's just, technically it's a substitution, but we're big kids now. We wouldn't do a substitution. You just know there's a 1/2 in front, right? Because your u would be a constant. You just factor out the constant, right? So you can actually do this. It's 1/2 x plus 1/2 sine 2x. Right? So that's what you do here. For this one, a similar thing. Think of this as a half of 1 minus cosine 2x. So this is a half of x minus a half sine 2x. Right? So for these guys, it's very important that you know, use the half angle formula. And this will work in general for even powers of cosine or sine, right? So if I had cosine to the 4th, just think of it as cosine squared squared, right? And then you start to apply this formula. So use this if you have integral of cosine to m x dx or integral sine of mx dx, and m is even, right? We do a different thing if m were odd, but you should know that. So I can do, oh, let's talk about when mx is odd, and we'll do more examples next time. If m is odd, right, and you're given that you have cosine mx dx over sine mx dx. Obviously, if your m is 1, we don't have a problem, right? It's a basic rule, right? But what if it's something like a 3 or a 5 or a 7, right? Example, a integral of cosine cube x dx. No, it's not cosine to the 4th over 4. You do that, you die. Okay. So the trick is to split this, right? You have a cosine squared x times a cosine. Now what?
Why cosine into cosine? Cosine squared.
Right, you change the cosine squared into 1 minus sine squared. Yeah, wouldn't do integration by parts. Remember, I think substitution way before I think integration by parts. Can a substitution work? Turns out I can, because I can change this to a sine, and now let u equals sine, right? Then my du would be that cosine. So then here, I would end up with u equals sine x, du equals cosine x dx. So then this integral becomes 1 minus u squared du. This is equal to integral of 1? U. You call yourself. A lot of students would write x here. Be careful. You do a substitution, there is no x anymore. Only u's now. And so the u would be sine. So this is sine q. That would be the answer. Okay. So let me just summarize that and then we can move on. So well, we can end the class. So if we have the integral cosine mx dx, and m is odd, and it's greater than 1, then factor of a cosine and use 1 minus sine squared x equals cosine squared x to change the remaining cosines to sines. Then substitute equal sines. A similar method works for integral of sine mx dx with n greater than 1 odd. Right? So if it's sine, you just factor off a sine and then change all the remaining signs to cosines and do substitution equals cosine. Right? So you think of this as sine of m minus 1 x times sine x dx. Here, change the cosines. This will be an even power, so you can use your Pythagorean identity. Change the cosines. And then u equals cosine x. Right? The du would give you that sine x, and then you can just do that as a polynomial. Yeah. For now, we'll stop there. We'll do a lot more on trig, including trig substitution later. But yeah, that's the start of 6.2. But again, for now, remember the hierarchy. Can a basic rule work? No. Can substitution work? No. Then you think other stuff, right? Obviously now you know if it's a trig function like this, you wouldn't think integration by parts. You're like, oh, I know how to deal with this, right? Whether the powers even or odd, I know how to deal with it, right? So then you'd skip the integration by parts in your brain because you know this, right? We know this. Okay. We'll